Okay, welcome to section 4.2, day 3, the longest section in the world. But actually, it does cover a lot of stuff. Now we're going to talk today about what are called antiderivatives. You're also going to hear me call antiderivatives integrals. Okay, and I don't know, I was always taught that they were integrals, but I guess the new word for them is antiderivatives. Because really, an antiderivative is actually more descriptive because it is the opposite of taking the derivative. Okay, when you have a function where the derivative is 0, they're constant, right? So if a derivative is 0, then the function equals c. Okay, all that means is that if you have a function equal to 6, the derivative of that function is 0, right? So you can really have any number and it's equal to 6. Okay, so functions with the same derivative can differ by a constant. If you take the derivative of this f function, if you take the derivative of this g function, you get the same derivative. Aha. So what this section tells us is that there is a c we can add to these functions which make them fit any type of function, okay? Any type of function would be their antiderivative, okay? So let's take a look at how we do this. Find all the possible functions where the derivative equals sine. Okay, well the function that gives us a derivative of sine is cosine. All right, so if we take the derivative of cosine, do we get sine? Actually, we get negative sine, right? So our function would actually be negative cosine. So negative cosine, I'm sorry, I don't need to write this derivative, it should just be f of x. Our function, which we take the derivative of, we get sine, right? We could have any constant on here. It could be a 0. It could be any number in the whole world. We still get the same derivative, right? So this is our answer. These are all the possible functions where the derivative is sine. So this is actually taking the opposite of the antiderivatives. On your purple sheet, we actually have a list of all the antiderivatives or integrals. Let's try another one. Find all possible functions whose derivative is 1 over x minus 1. All right, so what function gives me 1 over something? Aha, that's the ln function. So if I have ln of x minus 1, is that my derivative? I think so. I think so. Now all we do is add a c. These are all the possible functions where the derivative equals 1 over x minus 1. Okay, we are going to get a little bit more exciting than this. Find the function whose derivative is sine of x. Actually, we already did that. We know that that derivative is negative cosine of x plus c. And then this tells us the graph passes through the point 0, 2. All right, this is basically called an initial value problem. And what they do is we have figured out a function, right? We've figured out a general function. Now they're asking us for a specific function, one that passes through the point. So a specific function that includes 0, 2. Okay, so what we're going to do is this is our x, this is our y. We're going to plug it in and calculate c. Okay, so initial value problems, you're going to see these, they're always on the AP test. And with them we have to calculate c. So, in order to calculate c, we plug in the x and y. So 2 equals negative cosine of 0 plus c. All right, cosine of. Okay, if we continue to solve this for c, we get 2 equals negative 1 plus c. Add 1 to both sides, and c equals 3. Okay, final step, we're going to rewrite our equation with c equal to 3. So, function equals negative cosine of x plus 3. That is the answer to this initial value problem that gives us a specific starting point. Anti-differentiation is the process of finding derivatives. This is just kind of defining what we've just done. So they call this f prime of x is equal to the antiderivative for all x. Okay? All right, let's look at this using velocity and position. Let's say we have an acceleration and we want to find the velocity and position. Well, we take the velocity, 9.8 t plus c, all right, because remember the antiderivative of 9.8 is just 9.8 times t, or x, and we add c. Then what happens when we want to take this position? We have to actually divide by 2 and add an exponent. It's the opposite of the power rule. Opposite of power rule. Okay, so what we do is we add 1 to the exponent, and we divide by 2, or divide by exponent. And that's actually the new exponent. All right, so notice when we went from 9.8 to 4.9 t squared, we added 1 to the exponent, 1 plus 1 is 2, and then we divided 9.8 by 2. And then we took this second constant, we called it C1, just to differentiate it from C2. And we added a t to it, and then we added another constant. So sometimes we're asked to do multi-step problems using this technique. So let's try it with some numbers. Let's say that your acceleration is 9.8. All right, we want to find the velocity and position. Let's start with the velocity. Now notice, okay, so velocity function, the general function is 9.8 times t plus c. In order to find the c, they have given us an initial value. The velocity at x equals 0 is 1. So that means we have a point, 0, 1. So let's try 0, 1. 0, it's actually not x though, sorry, it's t. We'll try to keep consistent here. Oh, so t is 0, velocity is 1, let's fill in the rest. 9.8 times 0 plus c, so c must equal 1. All right, so now we have a velocity equation. All right, I'm going to move this and squeeze it. We have a velocity equation. Velocity equals 9.8 t plus 1. Now we're going to try to find our position. Look at, they gave us a point for position. All right, so our position equals 4.9 t squared. I added 1 divided by 2 plus 1t plus another c. Now we're going to take 0, 0 and plug it into here. So 0 equals 4.9 times 0 squared plus 0 plus c. Uh-oh, c equals 0 on this one. So our position function is this function, s equals 4.9 t squared plus t plus 0. All right, so our two answers are the position function and the velocity function. And we used our initial values. The velocity initial value 0, 1, and the position 0, 0. And that's it for section 4.2, day 3.